In this video, we are going to discuss the important questions, solution for the important questions from chapter number 2 that are in the previous past papers, 5 years papers. Starting from the first, that is on the page number 47, theorem 2.2. If f is differentiable at a point A is in domain of f, then f is continuous at A. It is given that f is differentiable and we need to prove that f is continuous at A. We know that a function can be continuous if its limit equals the direct function value. If we directly put the value of the limit in the function that will be equals to its limit, then the function is said to be continuous. So we know that if the function is continuous, then this equation holds. Now move it on the left side, we can write it like limit x approaches to a, f of x minus f of a equals to 0. Now divide it with x minus a and multiply it with x minus a. This now, after dividing and multiplying with x minus a, split the limit. It can be written as limit x approaches to a, f of x minus a over x minus a equals, here you have f of a. This is f of a into limit x approaches to a, x minus a. Now this is the definition of derivative of a function at a particular point. So we can write it like f dash of a, and we know that limit x approaches to a, if we put this limit here, this will give us the answer 0. So you observe this thing become equals to 0, and this is the same one as we wrote earlier, that if the function is continuous, then this line or this equation will hold, and you see this equation now holds. So we can say like thus f is continuous at a. Now come on the example number 1. Let f is from R to R defined by the function f of x is defined as the absolute value of x. Then f is continuous at a. X is equals to a. We need to prove that it is continuous, and you know that for continuity, the left hand limit, first of all the limit exists. The left hand limit must be equals to the right hand limit. If the limit exists, then put the direct limit and check its continuity. If at the first point limit does not exist, then you can say like directly like f is discontinuous. And after that, check whether f is differentiable at this point or not. You know that if a function is continuous, then we can just proceed on to check its differentiability. But if a function is not continuous, at that step we can just stop and write it like f is not differentiable. So by definition, we are starting from here, definition of derivative using the definition of derivative, limit h approaches to 0 at the particular point 0, f of a plus h, a here is 0, minus f of a over h. Now what is your f of x? It is absolute value of x. Replace x with this 0 plus h, you will get absolute value of h. Now f of 0, put the 0 here, you will get h 0. So only thing left is limit h approaches to 0, absolute value of h over h. Now check on it the left hand limit. If you approach it from the left side, h approaches to 0 minus, then your absolute value of h will be equals to minus h. And you know that minus h over h will give you minus 1. Now if you approach the limit from the right side, the absolute value of h will be positive h. Positive h divided by this positive h will give you 1. So you observe the left hand limit answer is not equals to the right hand limit. It means the limit does not exist. And we can say like it is not differentiable. Although it is continuous, it was given that the function was continuous. But since the limit does not exist, so it is not differentiable. Now we need to move on to the exercise 2.1. On exercise 2.1, we need to do question number 4. Is the function f defined by f of x, this function, piecewise continuous? If x is not equals to a, then this function you will consider. If x is equals to a, then 0 you will consider. You have to check whether this function is continuous and differentiable at this given point x is equals to a. Now to prove that whether it is continuous and differentiable at x is equals to a, we will just prove it continuous by definition. We know that if we are able to prove like f of x minus f of a mod is less than delta, let's suppose it is equals to epsilon, whenever x minus a mod is less than delta, then we can say like by definition the function is continuous at the given point. So for that purpose, we have to consider f of x minus f of a absolute value, and that is equals to, what is f of x? F of x is, consider this function, that will be x minus a into sine of 1 over x minus a minus f of a. At that particular point, the function value is 0. Mod, now this will be equals to mod of x minus a sine of 1 over x minus a. This can be written as mod of x minus a into mod of sine of 1 over x minus a. We can write it like this. Now we know that sine function is always bounded and it will be less or equals to 1. So it means if we just remove it, so we can write it like this whole function. This whole function will be less or equals to x minus a. If this bounded function becomes equals to 1, if this absolute function becomes equals to 1, then this whole thing will be equals to this thing. So I have written equality. And if it will convert, you see it is less than 1. So it could be negative as well. So if it becomes negative, then this whole thing will be less than this main thing. So we can write it as less or equals to x minus a mod. And this is less than delta equals to any number, constant number epsilon. Whenever x minus a mod is less than delta, whenever this number is less than delta, then this whole thing is less than delta. So we can write like, hence the function is continuous at x is equals to a. Now our first part is solved. Now we need to just prove it, like whether it is differentiable or not. For that purpose, use the definition of derivative. F dash of a equals limit h approaches to 0 f of a plus h minus f of a over h. This will be equals to limit h approaches to 0 f of a plus h. F of a plus h. What is your f of x? Your f of x is x minus a into sine of x minus a. Now here, replace your x with a plus h. Replace your x with a plus h. X with a plus h. You will be left with h sine of 1 over h. So here you will get f of a plus h. Here you will get h sine of 1 over h minus f of a will be 0. That is your this point divided by h. So this will become equals to limit h approaches to 0 h sine 1 over h over h. This h and h will be cancelled out. So it will be left with limit h approaches to 0 sine of 1 over h. And we know that this does not exist. So this implies that function is not differentiable. Function is not differentiable at x is equals to a. Now come on page number 66. Example number 10 is also a very important example. The solution is given here. You can just consult the solution. Now move on to exercise 2.2. First of all, I am going to solve this question number 4. That is, we need to differentiate all these questions that are given here in exercise 2.2. Starting from question number 4. We can just let this function as equals to y. Y equals sine of x under root. We can write it like sine of x raised to power 1 by 2. And this sine of under root, sine x raised to power 1 by 2. This 1 by 2 is on whole sine of x. And this 1 by 2 is just on this angle. Just keep it, remember. Now, we need to differentiate this function. Differentiating both sides with respect to x will give us dy by dx. This is in fraction form, so we need to just use the quotient rule. The square of the denominator, that is sine under root x whole square. Now this denominator will come as it is into d by dx of this numerator, that is sine of x raised to power 1 by 2, minus this numerator will come as it is, and the derivative of the denominator, that is sine of x 1 by 2. This will be equals to sine under root x, and now this term power down power minus 1. So we can write it like power down power minus 1 will give me minus 1 by 2. And then d by dx of without power minus this term can be written as it is. And derivative of this thing, we know that derivative of sine of this function could be cos of the same function, and the derivative of this angle, that is x 1 by 2, divided by this thing will be sine under root x whole square. This will come as it is. Now we can write it like, I am just writing it the numerator separately in the bracket. This main fraction is replaced with deviant sign, and the denominator I am writing it separately. Okay, this thing will give us sine of under root x, and now this term can be taken down. It will become 2 under root sine of x. I just moved it down because it has the negative power. Whenever we move it down, it will become the positive power. And d by dx of sine x will be cos of x, minus, I'm just first of all solving this main bracket. This is this main bracket. Minus under root sine of x cos of under root x, and derivative of this function. So here this derivative will be 1 by 2 power down power minus 1 will be minus 1 by 2. This main bracket divided by this thing, that is sine of under root x whole square. Now we need to simplify it. We will get here sine under root x cos of x divided by 2 whole under root sine of x, minus this thing can be written as whole sine under root x cos of under root x, and this thing can be written as 2 under root x, and this thing can be written as multiply by 1 over sine under root x whole square. Change this deviant sign to the multiplication so that we can write it in reciprocal form. This will become, now take the LCM here, we will get here under root x sine of under root x cos of x minus sine of x cos under root x divided by 2 under root x sine of x whole under root. I just took the LCM here, multiply by 1 over sine under root x whole square. Now we can just, this is numerator will be multiplied here with the numerator, and denominator will be multiplied here with denominator. So we can just combine both the fractions. It will be under root x sine under root x cos of x minus sine of x cos under root x divided by 2 under root x under root sine of x, and this thing can be written as sine square of under root x. So this is the answer for your question number 4. Now move on to the question number 7 of this, the same exercise 2.2. Let y is equals to arc tangent. Arc tangent is basically tangent inverse. Arc tangent x sine of alpha over 1 minus x cos of alpha. Differentiating both sides with respect to x, we will get dy by dx. Now derivative of, if we have y is equals to tangent inverse of x, then its derivative will be 1 over 1 plus x square, 1 plus angle square, and the derivative of the angle. So we will write it like 1 over 1 plus x is this whole angle. So it will be x sine of alpha over 1 minus x cos of alpha whole square into derivative of this angle, that is x sine of alpha over 1 minus x cos of alpha, like this. Now we need to just simplify it and use here the quotient rule. We will get here 1 over, take the LCM here, we'll get here 1 minus x cos of alpha whole square plus x sine of alpha whole square divided by 1 minus x cos of alpha whole square. I just took the LCM here, split the square on the numerator and denominator and take the LCM. Now the quotient rule, apply the quotient rule here. The denominator will be the square of the denominator. Now denominator will come as it is, and the derivative of numerator will give me 1 into sine of alpha, that is sine of alpha, minus, now numerator will come as it is, and the derivative of denominator, that is 0 minus cos of alpha. So it is minus cos of alpha like this. Now this we have a fraction 1 over this fraction, so denominator can be moved up here. If we just simplify it, we'll get 1 minus x cos of alpha whole square divided by 1 minus x cos of alpha whole square plus x sine of alpha whole square multiply by, now simplify these terms. If we simplify it, we'll get here, multiply, open the terms, we'll get sine of alpha minus x cos of alpha sine of alpha, minus minus will give me plus x sine of alpha cos of alpha divided by this same denominator as it is. Now this denominator can be cancelled out with this one, this term can be cancelled out with this term. Now it will be, and open this term as well. If we just simplify this term, in the denominator we will get, this is the numerator, sine of alpha, and in the denominator I will get 1 plus x square cos square of alpha minus 2x cos of alpha out of the first bracket, and the second bracket will give me x square sine square of alpha divided by equals this term. You know that cos square of alpha plus sine square of alpha is equals to 1. So I will get here sine of alpha over 1 plus x square minus 2x cos of alpha. So this is the answer for my question number 7. Now come on question number 15. Differentiate arc tangent this function with respect to this function. There are two methods to solve it. The first method is the simple formula, but that will be lengthy for you, and that is using the chain rule. Just let it equals to y, this function, let this function as equals to u, and find the derivative dy by du, that is equals to dy by dx multiply by dx by du. Separately take the derivatives with respect to x, put the values here and get dy by du. This will be the lengthy method by using the chain rule. The simple method, that is in order to reduce the steps, you can just adopt the second method, that is let this second function equals to u. Let u is equals to arc. Arc cos means cos inverse of x square. So this will be cos of u is equals to x square. Now let this function, let it equals to y. Y is equals to arc tangent means tangent inverse. Tangent inverse 1 plus x square minus under root 1 minus x square divided by under root 1 plus x square plus under root 1 minus x square. So this will be y is equals to tangent inverse. Now this is 1 plus x square. X square, you know, this is equals to cos of u. So you can write it like 1 plus cos of u minus 1 minus cos of u divided by under root 1 plus cos of u plus under root 1 minus cos of u. Now here I will use an identity. And what is that identity? You know that 1 minus cos of x equals 2 sine square x by 2. This is an identity, half angle identity. So just replace these terms with it, and 1 plus cos of u. 1 plus cos of u equals 2 cos square x by 2. Use these identities here in it. We will get y equals tangent inverse, and inside I will get here 2 cos square u by 2 minus under root 2 sine square u by 2 divided with under root 2 cos square u by 2 plus under root 2 sine square u by 2. So this will become, now square terms will be cancelled out. So this will become y is equals to tangent inverse under root 2 cos of u by 2 minus under root 2 sine of u by 2 divided by under root 2 cos of u by 2 plus under root 2 sine of u by 2. Now this under root can be taken outside common and cancel with each other. We will be left with y is equals to tangent inverse cos of u by 2 minus sine of u by 2 divided by cos of u by 2 plus sine of u by 2. Now we can just divide the numerator and the denominator with cos of u by 2, or the other method is take cos of u by 2 as common. We will be left with 1 minus tangent u by 2 because cos of u by 2 will come here in the denominator, so this will become tangent u by 2 divided by, take cos of u by 2 also common from the denominator, we will be left with 1 plus tangent u by 2 like this. This will be cancelled, so we will be left with y equals tangent inverse 1 minus tangent u by 2 divided by 1 plus tangent u by 2. Now we know that we can write it like y is equals to tangent inverse this can be written as tangent pi by 4 because we know that tangent pi by 4 will give us 1 in our answer, tangent u by 2. Now divided by 1 plus tangent pi by 4 tangent u by 2. This will not alter our this function, the previous equation. So y will be equals to tangent inverse. Now this is the formula for tangent pi by 4 minus u by 2. So now this tangent and tangent inverse can be cancelled out. So y will be equals to pi by 4 minus u by 2. Now we need to differentiate our this function with respect to this. This is y and this is u. So it means we need to find dy by du. So differentiate now this y function with respect to u. Differentiating with respect to u, we will get here dy by du is equals to 0 minus 1 by 2. That will be equals to dy by du is equals to minus 1 by 2. So this is the answer for our question number 15. Let's move on to the question number 18. That is y raised to power x plus x raised to power y is equals to c. We need to differentiate it. Now this is an implicit function. Now just separate it. Let this thing as u and let this thing as v. I am letting it u and letting it v. So I will get here u plus v is equals to c. Mark it as equation number 1. Or just take the derivative with respect to x. So we will get du by dx plus dv by dx is equals to 0. Mark this one as equation number 1. Now we need what? We need the value of dy by du by dx and dv by dx. For that purpose, what is my u? Let u is equals to y raised to power x. Now differentiating both sides, this will give me. Now in order to differentiate it, first of all, we need to just move this variable down. For that purpose, take the natural logarithm on both sides. This will be ln y is equals to ln yx, and you know that this is the property of natural log. If we apply it on the exponential function, the exponent will come down. So we'll get here ln y is equals to x ln of y. So this is u. Here we have u. So this thing will becomes ln u is equals to x ln of y. Now take the derivative. Ln u will give us 1 over u du by dx equals. Now we have a product of two variables here. So use the product rule. First of all, take the derivative of x. This will give me 1 second derivative as function as this. Plus, now first function as this, take the derivative of second function, that is 1 over y dy by dx. So this thing will become du by dx because for equation number 1 we need du by dx. So separate du by dx from here. This will become u times ln of y plus x over y dy by dx. What was our u? Du by dx equals u was y raised to power x into ln of y plus x over y dy by dx. We will use this value in equation number 1. Now we need dv by dx, so consider this v function now. Let v is equals to x raised to power y, this v function. Now differentiate it. Before differentiating, apply the natural log on both sides. Move it down, we'll get ln of v is equals to y ln of x. So this will give us, now differentiate it, 1 over v dv by dx equals, now first of all take the derivative of y, that is dy by dx, and ln of x will come as this, plus y will be as this, and derivative of ln x is 1 over x. So this will give us dv by dx, move it on the other side, equals v times ln x dy by dx plus y over x. This will be dv by dx equals, v was x raised to power y, ln of x dy by dx plus y over x here. Now use these two values in equation number 1. We will get using du by dx and dv by dx in equation number 1. We will get y raised to power x ln of y plus x over y dy by dx plus x raised to power y ln of x dy by dx plus y over x equals to 0. Now we need to separate our dy by dx. For that purpose, open the brackets. We will get here y raised to power x ln of y plus, this will be x into y raised to power x divided by y will give me y raised to power x minus 1 dy by dx plus x raised to power y ln of y dy by dx plus y x raised to power y minus 1 equals to 0. Now consider this as 1 and take the dy by dx common from it. Dy by dx times x minus 1 plus x raised to power y ln of y. Move the other two functions on the right side. This will be negative times y raised to power x ln of y plus y into x raised to power y minus 1. Multiply, this is multiplying here, divide it on the other side, so we will get dy by dx is equals to minus times y raised to power x ln of y plus y x raised to power y minus 1 divided by x minus 1 plus x raised to power y ln of y. So this is the answer for question number 18. Now I am going to solve question number 25. In question number 25, f of x equals e raised to power ax cos of b arc tangent of x. Here f of x is equals to e raised to power ax cos of b tangent inverse of x. Now differentiate both sides with respect to x. This will be f dash of x. Now we have two functions, so product rule. First of all, I am taking the derivative of this function, that is a e raised to power ax, and the second function will be as it is. Now write the first function as it is, and the derivative of second function will be minus times sine of b tangent inverse of x, and the derivative of this angle, is d by dx of b tangent inverse of x. Now f dash of x will be equals to, this can be written as a e raised to power ax cos of b tangent inverse of x. Now this negative sign will be taken outside, e raised to power ax sine of b tangent inverse of x, derivative of this thing, b is a constant, take it outside like this, and derivative of tangent inverse of x is 1 over 1 plus x square. Now we can write it like, take the e raised to power ax common, and this function will get e raised to power ax over 1 plus x square, and inside I will be left with a times 1 plus x square cos of b tangent inverse of x minus b sine of b tangent inverse of x. So this is the answer for our question number 25. Move on to the question number 26. That is, we need to differentiate f of x equals 1 over under root b square minus a square ln times b plus a plus b minus a divided by under root b plus a minus b minus a, and here we also have tangent x by 2 and tangent x by 2 here. Now we know that this is the property of ln. You can see like ln is applied on this whole function. This is the property of ln. We can just separate it. This is a quotient fraction. We can separate the ln into two parts as 1 over this function as it is. Now ln numerator minus ln denominator. So it will be ln numerator, that is ln under root b plus a plus under root b minus a tangent x by 2 minus ln under root b plus a minus under root b minus a tangent x by 2. So this is the property of ln. Now it will be easier to differentiate it. So the derivative will give us, differentiating both sides, f dash of x will be equals to 1 over under root b square minus a square. Now derivative of this function, the derivative of this function, I am writing it whole in this bracket because the answer will be too much, so that's why I am just using this bigger brackets here. Now ln function is 1 over that function, so it will be 1 over that function, that is b plus a plus b minus a tangent x over 2. Now d by dx of that inner function, that is b plus a plus b minus a tangent x over 2 minus this thing. Now the same thing, the same derivative you will use here, 1 over this whole function b plus a minus b minus a tangent x by 2 and d by dx of this whole function, that is b plus a minus b minus a tangent x by 2, and the bracket close. Now this thing will be equals to 1 over under root b square minus a square, this bracket we can write it like, now the derivative of this thing, the derivative of this thing is, we can write it like, it will be written as secant square of x by 2. You know that tangent inverse, tangent of x by 2 will give you the derivative secant square x by 2 and the derivative of the angle. So it can be written as this is a constant, this term will goes to 0, this term will goes to 0, and the here derivative will be, we will get here 1 by 2 under root b minus a secant square x by 2 divided by this function as it is b plus a plus b minus a tangent of x by 2. Now this negative sign, derivative of this thing will be minus 1 by 2 minus 1 by 2 under root this secant square x by 2. That minus and this minus will become plus. So we will get here 1 by 2 under root b minus a secant square x by 2 divided with this function, that is b plus a minus under root b minus a tangent x by 2. Now this terms can be taken common outside. We can write it like 1 by 2 under root b minus a secant square x by 2, this function as it is, and inside we will be left with 1 over under root b plus a plus under root b minus a tangent x by 2 plus 1 over the same function here as it is. Now take the LCM, we will get here b minus a secant square x by 2 over 2 into under root b square minus a square. After taking the LCM and simplifying, we will get here 2 into b plus a divided by the multiplication of these two terms. And the multiplication of these two terms will involve this formula. a plus b into a minus b, this will be a square minus b square. You have to use this formula here in the denominator, and after simplification you will get here b plus a minus b minus a tangent square x by 2 like this. Now we can write it like, we know that this under root b square minus a square, this is equals to under root b minus a into under root b plus a. So this will be cancelled out and this term will be cancelled out with this one. So we will be left with here, after simplification, the answer will be left as, here it will be secant square x by 2 divided by 2. This 2 and 2 will be cancelled out, so there is no need to write 2 here, into 1 over, open these terms, we will get here the terms b plus a minus b tangent square of x by 2 plus tangent square of x by 2. So this terms can be written as, we know that this is secant square of x by 2. Secant square of x by 2 can be written as 1 over cos square of x by 2. That cos square of x by 2 will be moved, can be moved out down, that I will show in the next step. This is b minus a tangent square x by 2 like this. The secant square of x by 2 can be written as 1 over cos square of x by 2, and the inside terms will be written as it is. Now move it inside, we'll get here 1 over b plus a cos square of x by 2 minus b minus a sine square of x by 2 here. Because you know the tangent square of x by 2, the identity of it, if it is multiplied with cos square of x by 2, will be left with sine square of x by 2. Open the terms. After opening in simplification, we will get here b times cos square of x by 2 minus sine square of x by 2 plus a here. And we can write it like 1 over a, this a plus b cos of x. So this is the answer for our question number 26. Now we need to move on question number 29. That is, take the derivative of f of x, that is equals to arc secant cosecant of x plus under root x. We know that f of x is equals to this secant, arc secant is secant inverse of cosecant x plus under root x. Now the derivative will be f dash of x equals, derivative of secant inverse of x is 1 over that angle under root angle square minus 1 and derivative of f, that angle. So it will be 1 over that angle as it is, cosecant x plus under root x into under root angle square, that is cosecant of x plus under root x whole square minus 1, and the derivative of that angle, that is cosecant of x plus under root x like this. This will become equals to 1 over cosecant x plus under root x and under root this whole function, that is cosecant of x plus under root x whole square minus 1, and derivative of this thing. Derivative of this thing will be cosecant x will give us minus cosecant x cot of x, and derivative of under root x will be plus 1 over 2 under root x. Now after taking the LCM, we'll get here, and after taking the LCM and simplification, multiply it with this fraction, you will get 1 over, okay, let's just write it first, then we will multiply it. Cosecant plus under root x into under root cosecant of x plus under root x whole square minus 1, and take LCM here, we'll get here 2 under root x minus 2 under root x cosecant of x cot of x plus 1. Now numerator will be multiplied with the numerator and denominator with the denominator. So we will be left with 1 minus 2 under root x cosecant of x cot of x plus 1 divided by 2 under root x times cosecant of x plus under root x and under root cosecant of x plus under root x whole square minus 1. So this is the answer for question number 29. Let's move on to the question number 48. That is also the important one. We have the implicit function arc tangent x plus y equals arc sine e raised to power y plus x. Now we need to differentiate this function. We need to find down the dy by dx here. For that purpose, differentiating both sides with respect to x, differentiate both sides with respect to x. we'll get here, this is tangent inverse of this function. So it is 1 over 1 plus x square, and x here is x plus y. So 1 plus x plus y whole square, and the derivative of this function. The derivative of this function will give us 1 plus dy by dx equals derivative of sine inverse of this function. That will be 1 over under root 1 minus angle square, and angle here is e raised to power y plus x whole square, and the derivative of this angle, that will be e raised to power y dy by dx plus 1. Now we need to take out this dy by dx. For that purpose, multiply these fractions inside, open the brackets. We will get here 1 over 1 plus x plus y whole square plus 1 over 1 plus x plus y whole square dy by dx equals, here we'll get e raised to power y over 1 minus e raised to power y plus x whole square dy by dx plus 1 over under root 1 minus e raised to power y plus x whole square. Now combine the values for this dy by dx, move it on this side and move this one on the right side. We will get here 1 over 1 plus x plus y whole square dy by dx. This function is written as this minus this one, e raised to power y over under root 1 minus e raised to power y plus x whole square equals this function 1 over under root 1 minus e raised to power y plus x whole square minus this function 1 over 1 plus x plus y whole square. Now take dy by dx common from this one. We will get here dy by dx times 1 over 1 plus x plus y whole square minus e raised to power y over under root 1 minus e raised to power y plus x whole square equal this function. Now we can just take the LCM here as well. We can write it like 1 minus e raised to power y plus x whole square times this function, that is 1 plus x plus y whole square, like this, and upside we will left 1 plus x plus y whole square minus under root 1 minus e raised to power y plus x whole square, like this. Also we can just take the same derivative here, LCM here, this will become dy by dx into, here we will be left with 1 under root 1 minus e raised to power y plus x whole square times 1 plus x plus y whole square, and inside we will be left with under root 1 minus in the numerator we will be left with this function e raised to power y into 1 plus x plus y whole square, like this. Now if you observe, write the same function here as it is. If we observe, we have the same denominators here. So these denominators can be cancelled out with each other. Now this thing is multiplying here, move it on the right side and divide it with this function. We'll get the answer for our dy by dx. So our dy by dx equals this function, numerator 1 plus x plus y whole square minus under root 1 minus e raised to power y plus x whole square divided by this function that will come down, that is under root 1 minus e raised to power y plus x whole square minus e raised to power y and 1 plus x plus y whole square, like this. So this is the answer for our question number 48. Let's move on to the question number 50 of the same exercise. This is also an implicit function, y arc sine of x minus x arc tangent of y equals to 1. This can be written as y sine inverse of x minus x tangent inverse of y equals to 1. Differentiating both sides with respect to x, we will use the product rule here. We will get dy by dx into sine inverse of x as it is. Now y will come as it is and the derivative of sine inverse of x is 1 over under root 1 minus x square. Minus, use the product rule here again. It will be 1 into tangent inverse of y, then the minus sign, the same minus sign, and x will be as it is, and the derivative of tangent inverse of y is 1 over 1 plus y square dy by dx equals to 0. Now combine the terms for the dy by dx, take the dy by dx common from those terms and move the other terms on the right side. This term and this term, I am taking dy by dx common from here I will be left with sine inverse of x minus x over 1 plus y square like this. Equals, move these two terms on the right side. We will be left with tangent inverse of y minus y over under root 1 minus x square. This can be written as dy by dx into 1 plus y square. This is 1 plus y square into sine inverse of x minus x equals, this will becomes 1 minus x square tangent inverse of y minus y over under root 1 minus x square. Now move this fraction on the right side. We'll get dy by dx equals this term, that is under root 1 minus x square tangent inverse of y minus y multiplied by this 1 plus y square divided by this under root 1 minus x square and multiply it with this term, that is 1 plus y square sine inverse of x minus x. So these were all the important questions from your exercise 2.2. Now from exercise 2.3, we can just consult this question number 2 part 4 that was came in the previous last year paper, that we need the differential to approximate cos of 61 degree. By following this method, you can also do this sixth part as well. So let's just do part 4, that is cos of 61. That is from exercise 2.3, question number 2 part 4, cos of 61 degree. You need to approximate it. Here let x plus dx is equals to 61 degree and let x is equals to 60 degree. Then this means your dx is equals to 1 degree. And you know that 1 degree is equals to 0.0175 radian. This is equals to this one. What you did, you just let this angle equals to x plus dx. Now nearest quadrantal angle, let's suppose that angle equals to x, and the remaining thing, like you see, 60 plus 1 will give you 61 degree. So the remaining 1 degree will be let equals to dx, and you know that 1 degree is equals to 0.0175 radian. Now let y is equals to cos of x. Taking differential of both sides, take the differential of both sides, you will get dy is equals to minus sine of x dx. So this will be equals to minus sine of, what is your x? Your x is 60 degree. And what is your dx? Your dx is 0.0175 radian. So this will be equals to, you know that this is negative. Sine 60 degree is under root 3 by 2 multiplied by 0.0175. Solve it using your calculator. You will get here minus 0.0151. Now this is your dy. Now you can write it like y plus dy equals, you know that this is your y equals to cos of x. If you just write it like y plus dy, this y plus dy, this will be equals to cos of x plus dy, and dy value is minus 0.0151. So this will be equals to cos of 60 degree minus 0.0151. This will be equals to 0.5 minus 0.0151. So the answer is 0.4849. So you approximated this cos 61 degree here. Now in exercise 2.4, you have to find out the root value, or you have to find the value of x up to 4 decimal places using the Newton-Raphson method. Question number 1, question number 2, question number 4. These 3 questions can be solved up, like you can use my previous videos Newton-Raphson method. Search the Newton-Raphson video from the playlist numerical methods or the numerical analysis from one of the playlists. The playlist is present here in the videos. You can search the Newton-Raphson method from that playlist of the numerical method. So just watch that video for solving the question number 1, 2 and 4. You can use that method. You can use that method for the remaining questions as well, but whenever you get some trigonometric function inside your equation for solving the Newton-Raphson method, you need to have some conversions in your calculator. So For solving question number 3, 5 and 6, I am solving question number 3 only. Follow that pattern for the question number 5 and 6 as well. And for the question 1, 2 and 4, follow the pattern of the question that is already uploaded as the name of Newton-Raphson method in the playlist of numerical methods. You can watch that. Now starting from question number 3, find the root for e raised to power minus x minus sine of x equals to 0, and you have to find down the root of the value up to 4 decimal places. Now how you can just fix your calculator? First of all, you need to fix your calculator according to the provided thing that up to how many decimal places you have to approximate your root. That is also mentioned in one of the videos of numerical method playlist, that how to fix your calculator up to some decimal places. Here in this question, you have to approximate, you have to fix your calculator up to 4 decimal places and then use your calculator. Otherwise, you will get the wrong answers. Now starting from question number 3, our function given here is f of x is equals to e raised to power minus x minus sine of x. Take its derivative. The f dash of x will be equals to minus times e raised to power minus x plus cos of x. This is the derivative answer here. Now using the Newton-Raphson method gives us xn plus 1 equals xn minus f of xn divided by f dash of xn. This is the general formula for Newton-Raphson method. You just memorize it and use this formula. Now x naught value is given here, that is 0.5. First of all, you have to do what? You have to fix your calculator here for 4 decimal places because it is mentioned. So you need to fix your calculator first, and then the next important thing, you have a trigonometric equation here. So don't use your calculator for direct calculations. Just convert your calculator from degree into the radian and then you can use the direct values. Don't forget to convert your calculator from degree into the radians. That I will show you in separate video, that how you can convert from degree into the radian. And then you can solve this question. Keep it in your mind. Don't solve this question in degrees. Solve it in radians after converting your calculator into the radians. I will show this thing in a separate video for you as well. Okay, first of all, your x naught is 0.5. Now your x1 will be, put n is equals to 0 here. For n is equals to 0 in equation number 1, you will have x1 is equals to x naught minus f of x naught divided by f dash of x naught. Now replace your function value from x naught. This will be x naught minus, function is e raised to power minus x, this will become e raised to power minus x naught minus sine of x naught divided by f dash of x naught. Use this value. This minus and this minus will become plus. So you will get here e raised to power minus x naught plus cos of x naught. Now replace the values of x naught here. This is 0.5 plus e raised to power minus 0.5 minus sine of 0.5 divided by e raised to power minus 0.5 plus cos of 0.5. This will give you 0.5, and here you will get, after simplification, the answer will be here 0.0856. This will becomes equals to 0.5856. You will solve it using your calculator, but don't forget to convert your calculator into the radians for this trigonometric function. I will show it to you in the separate video as well. Now your x1 is calculated. This one is your x1. X naught was 0.5. Now for n is equals to 1, in this equation you will have x2 equals x1. x2 is equals to x1 minus f of x1 divided by f dash of x1 here. So this thing will becomes equals to x2 equals x1 is 0.5856 minus f of x1. This will be e raised to power minus 0.5856 minus sine of 0.5856 divided by f dash of x1. You know that f dash of x, this negative and this negative will become positive, and your function will be e raised to power minus 0.5856 and plus cos of the same x1 value here. Now solve it using your calculator. You will get here x2 equals, after simplification using calculator, you will get 0.5885. You see, your root is still not repeated. When you will get the repeated answer, you will just stop it and you will say like this is your root. Now for n is equals to 2, you will get x3 is equals to x2 minus f of x2 divided by f dash of x2. So this will becomes x3 is equals to 0.5885 minus here f of x2, you will get e raised to power minus 0.5885 minus sine of 0.5885 divided by that minus, and that minus will give a plus e raised to power minus 0.5885 plus cos of 0.5885 here. So this thing will become x3 will be given as for you 0.5885. Now you observe you have the repeated root now, x2 and x3, the repeated. So it means the required root is 0.5885. So this is the answer for your question number 3 for this exercise 2.4.